As we saw in the last segment, the running time of an algorithm is measured as a function of its input size. So obviously algorithms will take more time on longer inputs, so the running time is an increasing function of the input size. Now we really care about the functional form of the running time much more than the details. So here in this graph I've shown you various functions and how they grow as n increases, and you can see that the function order 2 to the n basically grows so fast that it's out of the picture even for really small values of n. At the other extreme, the function log n grows so slowly that it's pretty much staying close to 0 for really large values of n, the values shown in the picture. So obviously an algorithm whose running time is like log n is much, much better than an algorithm whose running time is like 2 to the n, because an algorithm whose running time is 2 to the n is not going to be feasible even for reasonably small values of n. So now, in order to say that we want to focus on the functional form of the algorithm's running time and not on the details, one mathematically precise way to do this is something called the big O notation. It's one example of asymptotic notation. It's a way of comparing two functions just on their growth rate and not on their details. So for example, we can say that the log n function is big O, the log n function is big O of the 2 to the n function, because log n grows much more slowly than 2 to the n. So in a sense, big O is like saying less than equal to for functions. That's a very, very crude approximation of the truth. We have the converse of the big O, which is the big omega notation, where a function that's growing faster than another function is said to be big omega of the other function. So again, another way of saying this is that 2 to the n is big omega of log n. Okay, so that's the big O is like less than equal to, and big omega is like greater than or equal to. Let me give you some more examples. So technically speaking, this is a detail here. Order f of n, or for any function f of n, is actually the set of all functions whose growth rate is the same or less than the growth rate of f of n. So order n squared is a set of all functions that do not grow faster than n squared. Here are some examples of asymptotic bounds. So if you look at order n squared, it's a set of all functions that are of the same or grow as fast or less fast than n squared, slower than n squared. So 2n squared grows as fast as n squared, so it's order n squared. 100n squared plus n plus 1 is also order n squared, because the n and the 1 grow more slowly, and 100n squared is of the same order. 100n squared is of the same growth rate as n squared. Constants don't matter. Similarly, the function n grows strictly slower than n squared, so it's also in order n squared. Now looking on the other side, the lower bounds, 2n squared grows exactly as fast as n squared up to the constant 2, so we will say it's an omega of n squared. And this other function, n squared over 1,000 minus n, is also an omega of n squared, and n cubed is an omega of n squared. What's not the case is that n is not in omega of n squared, because n grows slower than n squared, and omega of n squared are all the functions that grow at least as fast as n squared. Okay? Similarly, here we can write n cubed is not in big O of n squared. Okay? So let's get back to the complexity of insertion sort. So we have that in order to solve the insertion sort on an array of n elements, we've solved the problem already on an array of n minus 1 elements, that's t of n minus 1, and then the last element may need to be swapped all the way to the beginning. That could be as many as n steps. So we can write t of n equals t of n minus 1 plus n, and if you use telescoping, you will find that t of n equals n squared plus n over 2, which, by what we've said earlier, is order n squared. So insertion sort has a runtime of order n squared. But we've only expressed the running time of insertion sort as a function of the input length. We have to realize that there can be many different inputs on which insertion sort is used. So let's look at the code again. Have this code in mind, the pseudocode. and then look at how this algorithm would perform on an array that's already sorted. So here's an example, the array 1, 2, 3, 4. You find that the outer loop, every time we run the outer loop, the inner loop is immediately finished, because what does the outer loop do? It moves the red barrier from the leftmost point to the rightmost point, and it tries to take the one element that's to the right of the barrier and place it in the right place on the left. Well, as soon as it picks up that one element, it's already in the right place because the array is already sorted. So the inner loop terminates immediately. So basically the running time of insertion sort on this array, the inner loop takes only one step, and the running time of insertion sort is just the n iterations of the outer loop that have to happen, each taking one step, giving you order n. So what's going on? On the earlier slide, we just said that insertion sort takes order n squared time, and here we're saying it takes order n time, which is the right answer. This raises the point that there are many inputs of the same length, and an algorithm might be very fast on some of these inputs and very slow on some of the other inputs. In computer science, especially in the theoretical part of computer science, we always take the pessimistic view that the input will not be favorable to us. We will have to have an algorithm that does well even if on the worst case input. So we cannot assume anything about the input, so we'll always assume the worst case. And so we should say that insertion sort takes order n squared time. Okay? So let me pause for a minute to make sure that you've gotten both of these recurrence relations, because we're going to move on to one more new paradigm for algorithm design on the next slide. We're going to talk about algorithm design by divide and conquer. So here what we're going to do is we're going to take a big problem and split it into pieces, roughly equal pieces it'll turn out, solve the little pieces by themselves, and then put the solutions back together. It's the same idea as the previous segment showed. Basically, in the previous segment, we said in order to solve a problem of size n, we use the fact that we know how to solve a problem of size n minus 1 and build from there. Here, what we will do is, rather than go to problems of size n minus 1, from a problem of size n, we will create two problems of size about n over 2 or so. And it will turn out that this is good for efficiency. So again, the paradigm for insertion sort is illustrated by this picture. You have a problem, you divide it into sub-problems, you do a conquer step where you solve each of the sub-problems, and then you combine the solutions to solve the whole problem. We'll again give examples of this, but this is the divide and conquer paradigm. Divide the problem, conquer each of the sub-problems, and combine the results. Okay, in general in this course I want to say something. This course is not only about teaching you specific algorithms that are out there, but for you to be able to come up with algorithmic solutions and to learn the tools that are being used here. So even though I'm going to give you examples of divide and conquer algorithms, I would like you, as soon as I state the problem, perhaps to pause the video and think for yourself, how might I solve this problem using divide and conquer? This will be difficult in the beginning, but if you keep trying, hopefully by the end of the course, you will not need to see the solution that we present, but instead be able to come up with your own solution. I'm going to illustrate the divide and conquer paradigm by an artificial puzzle-like problem, but I think it does a great job of illustrating the paradigm, and that's why we are using this example. So imagine an n by n grid, as shown in the picture here, which has one tile that's a hole. Basically, the rest of the grid is filled, and there's one tile that's a hole. You want to tile this grid by these triomino tiles. What are triomino tiles? They are tiles that are L-shaped, and they correspond to three grid squares. So you have these kind of tiles, and you want to tile the entire grid using these tiles. What does tiling mean? Every square in the grid must be covered by one of these triominoes, and no triominoes should overlap. That's what tiling means. And we want to show that we can always do this and come up with an algorithm for doing it. Let's imagine that n, the size of the grid, is a power of 2. This should be capital N, is a power of 2. So how would you do this? So the divide and conquer paradigm would say, let's divide the grid right down the middle, both horizontally and vertically, into 4 subgrids. Now, one of those subgrids, this one here has the hole in it. So that's the hole. The other 3 subgrids are complete. The original problem was to tile a grid which had a hole in it, which is perfect for this subgrid, which is exactly the same problem for this subgrid, but these other 3 grids are not looking like the original problem. How do we fix that? Well, let's put a triomino right here. So this part is covered by a triomino. And now look what we have left. We have 4 subgrids, each of which has a hole in one place. And so if we can solve this problem, we can solve the bigger problem as well. So we've reduced the problem of solving the bigger square, tiling the bigger square, into the problem of tiling 4 smaller squares of the same form. And we keep doing this until we get to the base case. The base case will be a 2 by 2 grid with 1 square missing. So there's a 2 by 2 grid with one square missing, and obviously you can tile it with a triomino very easily, just like so. So essentially we've taken a large grid, broken it up repeatedly, put a tile in the middle every time we break it up, and shown that we can tile the large grid in this manner. That's divide and conquer in action. So we divided the big problem into 4 smaller problems. We conquered these sub-problems by actually figuring out how to solve them. And after we've solved these sub-problems, the combined step was rather easy here, because the combined step was just to take the union of all the solutions to all 4 sub-problems.